is defined by x of t equal to x naught plus mu t plus sigma wt. Here this one demonstrates how this process goes through time. Here wt is a Wiener process, and the coefficient mu of t is called drift coefficient, and sigma is known as volatility coefficient. The following indicates the key properties of this Wiener process. Linear Wiener process is a normal distribution with mean x naught plus w naught, where x naught is the starting point and sigma squared times t is the variance of the process. Furthermore, the difference between xt and xs, when t and s represents a different time, or this is the increment, is given by this one. Hence, the increment is also a normal distribution with mean mu times t minus s and variance sigma squared times t minus s. Remark that the difference delta x for linear Wiener process is given by this expression in mu times t minus s and variance sigma squared times t minus s. Remark that the difference delta x for linear Wiener process is given by this expression. The expectation is, as we already say, this mu times t minus s. The variance is sigma squared times t minus s. Next, the geometric Brownian motion or geometric Wiener process is defined by this expression, that is st equal to s naught times e to the power of mu t plus sigma wt, or e to the power of xt, where xt is just some expression which is a logarithm of s naught plus mu of t plus sigma wt. Here you can see the process representing geometric Brownian portion just for four samples for different parameters mu and sigma. Here x of t is linear Wiener process with initial value equal to logarithm of s naught. Mu is the drift coefficient for x naught, as well as sigma is the volatility coefficient for xt. The other property is the distribution property of a geometric Wiener process. The geometric Wiener process is log normally distributed with mu, or the expectation logarithm of s naught plus mu times t, and the variance is sigma squared times t. Of course, we can calculate that from the property of logarithmic distribution. The expectation of st, or the expectation of the geometric Wiener process, is given by this expression. Also, the variance is given by this expression. Remark that the geometric Brownian motion or geometric Wiener process is a a long-standing model represents risky asset price movement, and also it underlies the Black and Scholes-Morton and aids in generating economic scenario for banking and insurance. Furthermore, ST divided by S small t is log normally distributed because of this expression here, as you can see. Let us look further properties of linear process and geometric Brownian motion. For that, let us revise first what does it mean by log normal distribution. When we say log normal distribution, a random variable x is said to be log normal distribution with this parameter. This means log normal distribution with this parameter if it specifies that the logarithm of this x is normally distributed with mean, mu, and variance sigma square. The other very important thing is that if you calculate the expectation of this log normal distribution, you will get e to the power of mu plus sigma square over 2 by the moment generating function. Moreover, the variance of log normal distribution is given by e to the power of 2 times mu plus sigma square times e to the power of sigma square minus 1. Now recall that the linear Brownian motion is given by x naught mu times t plus sigma wt. Here, if we calculate the expectation of this xt, you will get x naught plus mu times t, because the expectation of the Brownian motion is 0. Also, if you calculate the variance x of t, the variance of this one is 0. The variance of this one is sigma squared times the variance of wt, which is equal to this one. Because the linear Brownian motion here is generated by the randomness of this Brownian motion, then it is also normal distribution. Therefore, it is a normal distribution with mean, this one, and the variance given by this one. If you look at the increment of this linear Brownian motion by direct calculation, it is x naught plus mu t plus sigma wt minus again x naught mu s plus sigma ws. Then this is 0, so mu t minus s plus sigma wt minus ws. This obviously shows that the increment is also normally distributed with this expectation and this quantity variance. For the case of geometric Brownian motion, which is defined by st e to the power of mu t plus sigma wt, or e to the power of logarithm of s naught plus mu t plus sigma times wt. We denote this by xt. This xt is linear Brownian motion with the initial value equal to this one. Obviously, this is the same as writing logarithm of s naught plus mu times t plus sigma wt is equal to logarithm of st. Since this one is normally distributed, you can say that st is log normally distributed with parameter this one and this one. Then using the property of the expectation of logarithmic distribution, which we already given here, by the same by inserting the important parameters, then the expectation of st is equal to s naught e to the power of mu plus sigma square over 2 times t, and the variance of this log normal distribution is equal to s naught square e to the power of 2 mu plus sigma square times t times e to the sigma square times t minus 1. Also, if we look at this quotient st over s small t, by the definition, e to the power of w capital T plus sigma w capital T divided by s naught e to the power of mu times t plus sigma dt. Cancel this. This is just equal to e to the power of mu times capital T sigma times capital T minus small t. Since this one is normally distributed, then st divided by s small t is logarithm log normal distribution. Is normal distribution with the parameter, of course, mu times capital T and sigma square capital T. Here we will simulate the linear Rayleigh process or Brownian motion using Python code on Google Colab. So the stochastic process is given by this, as you see, and in its discrete form it is given by this one. As usual, we start by importing important package like numpy as np. Also we import matplotlib.py plots as plt. Then we define a function called linear Rayleigh process. So the inputs for this function is capital T, usually indicating a time horizon, capital N, number of trading days in the case of finance, and the process starts from x0 and mu, sigma. These are the parameters. So this is a comment, as you know. That means a function for generating a linear Wiener process. So first we discretize the time t and p is equal to linear space of 0t. This one divide the interval given by 0 capital T into n equal periods. Next, we start by creating empty list. This is just an empty list. Okay, empty list. And then again also dt, this is a time step, which is the first component of time minus the second component of time minus dt is equal to the second component of t minus the first component of t. This is just the time step. Then x dot append, that means we insert the initial value at the end of the empty list. Then we use the for loop for I in range of 1 to length of t. Then the next x will be x next equal to x I minus 1, the previous x plus the change, which is equal to mu times dt plus sigma times square root of 80 times a random number or a sample generated from random normal. Then again we append our list by this x next. Then the function returns x and t for the process of plotting. So these are example parameters. Example let's say t is equal to 1, n is equal to 252, and mu is equal to, that means the diversity is 0.2, and the sigma, let's say 0.1, and the process starts from, say, 10. Call the function, here, that means with this parameter, call this function. We can copy and paste here. So the output x and the t. So then we can plot ELT plots t versus x. X label ELT y label. Just let's see, grids on, and then show us the plots. So this is just an example of linear Brownian motion. Now let us see geometric Brownian motion, simulation of geometric Brownian motion. In this case, let us see the help of this Colab AI. This is just an experiment I didn't see until now. I hope this will help in saving a lot of time. So let us write this prompt: simulates geometric Brownian motion. Wow. So this a code is generated, and it says use code with caution. And interestingly, the code is provided for us. This will definitely reduce the time for coding, but our task is here to check whether it is correct or not, and we have to use it carefully. The assistant is very nice. Amazingly, the AI imitates the code we already written for the case of linear learning process here. Even it writes the function in the same way, as you can see, geometric Brownian motion, and the inputs are almost the same, but it uses in the same way as we did in our note S here. And the description, a function to simulate geometric Brownian motion, is used. So the way t is discretized is the same, the way it creates empty list, the way it creates dt or the time step, and it append the initial value s naught, and the way it creates the for loop is also similar with our code in the previous. So this is geometric Brownian motion, and the output you can see is S and T. Further, it provides an example: time is equal to 1, and 252, S naught starts from 100, the mu is 0.05, sigma the volatility, then in the same way it gives the plots. Let us run this one. So exactly, this is a geometric Brownian motion. So there is an assistant for us, and definitely our task will be checking the concept and making sure that everything is accordingly.